son ejemplos de oportunidades y desafíos de la ingeniería a nanoescala y el desarrollo de nanomateriales. Las últimas 2 décadas han sido testigos de fascinantes avances en nanotecnología, con sus manifestaciones en muchas áreas de la ciencia y la tecnología. Y para charlar de todo esto, contamos hoy con 2 referentes en la materia. El profesor Pulikil Ajayyan, que nos va a hablar de varios aspectos de la nanotecnología, como son la síntesis, ensamblaje y uniones a nanoescala, las nanoestructuras híbridas, los nanocompuestos, las membranas o los materiales funcionales. A continuación tomará la palabra el profesor Ramón Torrecillas, que entrevistará al profesor y mantendrá con él una conversación en la que ambos especialistas discutirán sobre las oportunidades y desafíos inherentes que se avecinan en el desarrollo de tecnologías basadas en nanomateriales. And now, let me switch to English. Good afternoon and welcome to the program The Usefulness of Science, co-organized by the Consejo Superior de Investigaciones Científicas to the European Union and the Instituto Cervantes of Brussels. In this second meeting of our program, we will go into the world of nanoengineering. The last 2 decades have witnessed fascinating advances in nanotechnology, which have had ramifications in many areas of science and technology. It is an honor for us to receive our guests today, 2 world-renowned scientists such as Professor Pulikil Ajayyan and Ramón Torrecillas. In his talk, Professor Pulikil Ajayyan will focus on several aspects of nanotechnology, such as nanoscale bonding, nanocomposites, membranes, or functional materials. Afterwards, Ramón Torrecillas will interview him, and both will discuss the opportunities and challenges related to the development of technologies based on nanomaterials. Profesor Ajayyan es un pionero en el área de la nanotecnología. Su trabajo cubre diversas áreas de nanomateriales como nanopartículas, nanotubos de carbono, materiales bidimensionales, nanocompuestos y materiales de almacenamiento de energía. Ha publicado más de 1000 artículos que cuentan con más de 100.000 citas. Es profesor de ingeniería en la Universidad de Rice en Estados Unidos y fundador de su departamento de ciencia de los materiales y nanotecnología. Y ha sido galardonado, entre otros, con el Spears Memorial, la medalla de Materials Research Society, el Alexander von Humboldt-Hellsman y el Lifetime Nanotechnology del Centro de Tecnología de Houston. Profesor Ramón Torrecillas es el delegado institucional del Consejo Superior de Investigaciones Científicas ante la Unión Europea, es doctor en Ciencias Físicas por la UNED, en Ingeniería de Materiales por el l'Institut National de Sciences Appliquées de Lyon. Ramón además creó el Departamento de Cerámica y Refractarios del Instituto Tecnológico de Materiales de Asturias en 1991, del que fue nombrado director, y en 2007 impulsó la creación del Centro de Investigación de Nanomateriales y Nanotecnología, el CIN, un centro mixto del CSIC de la Universidad de Oviedo y del Principado de Asturias, del cual además ha sido director hasta el 2008. Fundó además la empresa Nanocare Research, dedicada a la fabricación de cerámicas técnicas avanzadas, nanocompuestos y nanomateriales. Tiene más de 200 publicaciones con alto impacto, 17 patentes, de las cuales están 9 en explotación. Professor Pulikil Ajayyan is a pioneer in the area of nanotechnology. His research covers several areas in the field of nanomaterials, such as nanoparticles, carbon nanotubes, two-dimensional materials, nanocomposites, and energy storage materials. He has published over 1,000 papers, thereby getting over 100,000 citations, and he's professor of engineering at Rice University and founder of the Department of Material Science and Nanoengineering. He has been awarded the Spears Memorial, the Materials Research Society Medal, the Alexander von Humboldt-Hellsman, and presented with the Lifetime Nanotechnology Award at the Houston Technology Center.
Hey.
¿Se oye? Sí.
Ahora sí.
Okay. Professor Ramón Torrecillas is Institutional Delegate of the Higher Council of Scientific Research to the European Union. He's PhD in Physical Science from the UNED and PhD in Materials Engineering from the Institut National de Sciences Appliquées Lyon. In 1991, Ramón Torrecilla set up the ceramics and refractory department at the Asturias Technical Institute for Materials, where he was appointed director. In 2007, he promoted the creation of the Nanomaterials and Nanotechnology Research Center, a joint initiative by the... That's right? Can you hear me?
Now
okay,
yes.
Sorry.
Let's go back.
It's about technology. He's the founder of NanoCare Research, a company dedicated to the manufacture and advanced technical ceramics, nanocomposites, and nanomaterials. He has written than 200 high impact papers, and
No.
There's a signal problem with that.
She's the only one who have the problem.
It appears so, yes.
Yeah.
One and her?
Well, in any case,
Yes.
I think Professor Azarian can start probably.
Yes.
Okay. Should I start?
Okay. Please, can you share your...
Yeah, let me share my screen.
Okay, thank you.
Okay, the moment you give me a go ahead, I will start.
Go ahead, Azarian.
You can see my screen as well, right?
Perfect.
Right, yeah.
Okay, so good evening to most of you who are in Europe, and it's about midday here in Houston. Thank you for inviting me for this. I think it's important that many of our scientific advancements are conveyed to the general public. And I really think that this is an important thing that you're doing to let people of different disciplines talk, and hope the public understands the importance of science. And in that regard, let me just start by saying that I hope everybody is safe, wherever you are. This has been an amazing, very interesting year for most of us. And we owe to technology to actually be able to do something like this. Not only that we have been able to communicate, in a very different type of style through things like Zoom and online. It really is a testimony to what we have done in terms of ingenuity and scientific advancement. So I think it's really, something that we all need to be proud of. Now, I come from Houston. I'm at Rice University. It's a university about 100 years old. And of course, it's a small private university in the middle of a big city, Houston. For those who are not familiar, we are in the south central part of the United States. It's considered to be the energy capital, at least the traditional energy capital. Most of the oil and gas companies have their headquarters in Houston. And also, it's a sprawling city with a lot of healthcare technologies as well. I'm sure that NASA is also close. So it's got a lot of flavor in terms of technologies. In a very diverse city and of perhaps 5 million people. So I'm going to talk today to a broad audience. So it's going to be, kind of a broad lecture in terms of discussing topics that are materials oriented, but at the same time, I hope it relates to a lot of people who are attending. And I'll try to make it as simple as possible. You get a flavor of what nanotechnology is all about. And I have been in this field for about years now, and lots of things have happened. And again, I hope we'll have a nice discussion with Ramon later on in terms of the impact, where we go with this type of technologies and how it has changed in certain areas of technology. So once again, let me again start with another quote from Michio Kaku, who says that our destiny is to become like gods we once worshipped and feared, but our tools will not be the magic wands and potions, but the science of computers, nanotechnology, artificial intelligence, biotechnology, and of course, quantum theory. The reason why I chose this is because nanotechnology prominently features in this quote, and for a good reason. Nanotechnology, again, 20 years old from its inception, has become an enabling technology that will feed into a lot of different areas of future devices and structures and so on. So it has got that breadth that makes it compelling for many people to have somewhat an understanding, whether you're working in biotechnology or whether you're working in electronics, nano has and will have an impact, and hence it's a very broad area that like us cover. And now, as a very, very, very basic introduction, let me say that nanotechnology is all about things at a very, very small scale. And for a benchmark, DNA is about 2.5 nanometers in diameter. And so it's really at a scale where there are structures that are very functional. But at the same time, it's a scale which is rather difficult to manipulate and, again, to understand and to kind of play around with. That being said, if you look at technologies, semiconductor industry has always been a driver. We are, in fact, talking about length scales in the 7 nanometer and less regime. So today's device technologies have been able to control matter at that scale on a very large scale, in a scalable fashion, which is again remarkable. And this technology over the last 2 decades have developed to a point where we can really manipulate and control matter at that scale. That really tells something about the progress in these areas. So end of the day, we are talking about scales which involves a few tens of atoms, and that is really amazing. Of course, historically and over a long period of time, people have, knowingly or unknowingly played around with nanotechnology. Example is in the picture that you're seeing, in the stained glass windows and these kind of artifacts. People had always been, embedding nanomaterials. And in fact, it's very interesting. Even the colors that you find are all a matter of how small particles of metals that you can create. That gold, which is yellow in bulk, changes colors as you go to smaller and smaller scale. So by breaking down salts which contains metals using chemicals, people were able to make nanoparticles that are really small so that you actually get different colors, which is a result of the plasmons that exist in these materials or electrons. And that really shows that people have been processing and doing nanotechnology for a very long time, although not really understanding how these things come about. And scientists like us is in the process of understanding some of these things and going beyond what they could do to be able to control things at that scale. Well, before I start giving examples and so on, I still want to say a few things in a background. A couple of things that are very important, especially in terms of processing and manufacturing. And this has to do with how we create material with that scale. Obviously, you have seen that today semiconductor industry can make things that very small, but they do this by machining things down from top to bottom, top down, we call it. So you can have larger structures, and you use techniques and tools to make things smaller and smaller. All the way to 7 nanometers, as you saw in the previous slide. So that's a traditional way of making materials and structures. Of course, it's also very fascinating to see if you take a certain volume of matter and break it down to smaller and smaller sizes, you start seeing this remarkable change in how these behave. For example, 1 centimeter cube material that has a 6 centimeter square surface area if you break it down, the same material into 1 nanometer cube, you have 60 million centimeters square of surface area. So it's a very different material for lots of us. You know, it has not changed the amount, but it has changed its form, its morphology, its interaction with the surrounding. So it becomes something entirely different. And this is one aspect that you have to always bear in mind when you go to that kind of scale. The challenges that is involved in manipulating, processing, understanding, they're all quite. Then there is the other approach, which is essentially the bottom-up fabrication, which actually biological systems have always part of this, where you build stuff from molecules up or atoms up, and how much control you can have is a matter of what kind of tools or what kind of approaches that you take doing this bottom-up manufacturing. Here is a beautiful image that kind of shows the crux of this matter. Essentially, using a scanning tunneling microscope, they were able to push atoms into a particular structure, what they call a quantum coral, showing all these standing wave patterns that is coming from the electrons in these atoms. So this is kind of the ultimate goal for all of us, to make materials with the precision of every atom that you put into that material. Of course, we have not reached that point yet, but this is essentially what we are trying to do. How do you build structures and materials with atomic precision? And how do we assemble these things together? How do you make, build these pathways from nanoscale to macro scale so that you can have control at every stage? These present two diverse ways of putting things together, the top-down approach and the bottom-up approach, and both are valuable. Of course, in the case of bottom-up fabrication, we are still learning the rules of the game, and hopefully there will be a stage when we will be able to build things with atomic. Now, there has been some beautiful discoveries along the way in the past 20 years or so. Let me start with this particular one because it happened at Rice University, and it received the Nobel Prize in Chemistry in 1996. Obviously, of course, this is not the discovery of a soccer ball, but it is discovery of something called the fullerenes, carbon-60. It actually is 60 atoms of carbon beautifully packed into what we call an icosahedral symmetry, one of the best symmetries you can build. And essentially, these structures were seen to be a unique form of carbon at that point, in 1996. Just like any other discoveries, a lot of people had difficulty believing it in the beginning, but then when these were synthesized and produced in large, people were able to understand by doing experiments with a large amount of these C60. So this is, again, is essentially the starting point of nanotechnology in some way, because people were able to imagine that using well-known materials like carbon, one could still explore uncharted territories and create structures that have very specific properties and very beautiful outcomes. So this was, again, a good example of the beginning of nanotechnology discovery. And with the same kind of carbon, things progressed and people found different morphologies, different structures of carbon. And again, it resulted in another Nobel Prize in 2020 for discovery of graphene, or the same material that was used to build the carbon-60. One was able to exploit the structure of these type of materials, graphite, and extract atomically thin layers from this, and again do experiments on those extremely thin material. And again, there are some amazing physical attributes and physics properties for these graphene-like material, extremely high mobility for electrons in these systems, and there are many other things that are probably more detailed. But the fact that you were able to create a freestanding two-dimensional structure, just a single atom thick, and explore the properties of this was a remarkable thing. I will talk about this later on related materials that we do. And somewhere in between the 2-dimensional and 0-dimensional structures that I showed you, for the same carbon again, people also discovered what is called carbon nanotube. And essentially, these were just a layer of graphene that was folded into a beautiful cylinder. But the discovery was interesting because what people figured out is that by a slight twist during this folding process, one could introduce a structural chirality, or how the hexagonal arrays go around the cylinder. And this chirality had a strong effect on the electronic properties of this material. And this was very, very much a surprise at that point in the early 90s, because for the first time, something like carbon, which was either an insulator, for example, in diamond, or a semi-metal in the case of a graphite material, these type of structures essentially proved that you could have semiconducting carbon. You could have, metallic, highly metallic carbons and so on. So again, there are two attributes that came together. One, of course, is the structural changes that you can build into a material. And the other is the dimension. So a combination of this dimensional aspect and the structural aspect allows you to make lots of materials that go beyond their traditional bulk properties. And that is why this kind of materials become so interesting. Again, as a material scientist, this is what we do. We explore properties of materials, but we also try to build new materials that has unique properties and that could be adapted to emerging technologies. Now, carbon nanotubes is fascinating for a lot of people, for a lot of people. And there were all kinds of fascinating ideas that were proposed. And this was one. Richard Smalley, who was a Nobel Prize winner from Rice, he used to say things like, I would like to make a very long fiber with nanotubes because nanotubes are extremely strong, and go fishing with it. Or, there were people who were suggesting that you could, in fact, build a space elevator using something like nanotubes. For a good reason, because carbon-carbon bonds are extremely strong, and this is probably the only material that is viable for something as beautiful as a space elevator. But the point I wanted to make is that there is a major challenge as you go from the fundamental properties of materials at nanoscale and how they scale as you build larger and larger structures. Typically nanotubes are, a few nanometers in diameter and several hundreds of microns long, but that's not good enough for making a space elevator. You need to have, miles and miles long these type of fibers. And in order to do that, you need millions and billions and trillions of nanotubes to put together into these macroscopic entities. And then the problem arises. Then you lose properties along the way. So interface becomes a deciding factor in many of these things. And I will talk later on about these specific interfaces that are important. How do you conserve the properties as you scale or as you build things together? How do you assemble these things together? These are some of the important challenges that face nanotechnology. That being said, there's been tremendous advances. Here is a colleague of mine, Professor at Rice, who has been spinning these nanotubes into spools or almost continuous fibers. And you can actually make very long fibers with reasonably good mechanical properties. But still the goal of creating a space elevator or a long fishing rod is still, outstanding. And that's because of these engineering problems that you face as you put nanostructures. Another aspect of nanotechnology is found in nature. Nature has done amazing things with nanotechnology. And here is a great example. It's actually an abalone shell. And, this is almost the same material that chalk is made of, calcium carbonate. 99% of this material is calcium carbonate. But there's a big difference between chalk and an abalone shell. You break this material because of the way it has been engineered. So the trick is in the kind of engineering that goes into structures like this. Essentially, these calcium carbonate platelets in the submicron scale or nanoscale has been sandwiched between protein molecules or soft material to make these brick and mortar kind of arrangement, which makes it extremely tough. Essentially, the idea is that because there are so many of these interfaces, if you create a crack, the crack gets deflected at every one of these interfaces, and ultimately it takes enormous amount of energy to break this. And that makes it super tough material. So the same material that is very brittle, as in chalk, can be made into something like this with a small amount of additive and the right kind of engineering, especially at the nanoscale. So that again shows the beauty of nano engineering in all its glory. There is another thing that also plays well to the nano engineering, and that's also found in nature, and that's hierarchy. You know, when you do things bottom up, as you start to build things from bottom up, it's much easier to introduce hierarchy when you build it. So something like, you know, a plant, you know, or the body of biological systems, you start with really small fibers made from glucose and other types of molecules, and you start creating these nanoscale fibers, and then to micron scale and to larger scale. So at every stage of this structural variation, you can introduce functionalities, you can introduce surface changes, which means that this hierarchy plays in very well into the overall structure that you create. And this is only possible, or at least, you know, it's much easier to do when you do this bottom-up fabrication compared to the top-down. And that also is the reason why the bottom-up approach is very, very valuable, because you have lots more flexibility in creating interfaces and modifying interfaces as you build these. And I'll give you one more example of the nature of nanotechnology or nanotechnology in nature. This is the geckos. You know, we have always been fascinated by geckos, why they are sticking up on the you know, roof and not falling down. And it has nothing to do with you know, a very sticky stuff. It is actually to do with nanotechnology. It's the way the feet are covered with these micron scale fibers, which further you know, split into submicron scale fibers, almost to the nanoscale. So when they place their feet against the wall, there is enormous amount of contact area because of this nanoscale size of the fibers, and that van der Waals force is, you know, enough to make them hold their own weight. Of course, and also it's nice because you know, since it is not an irreversible sticky business, you can actually quickly change the orientation and change the contact forces so that it can actually move again. So it's a marvel of nature that it has evolved to do things like this by using nanotechnology as a tool. So I think I have given you several examples why, you know, nanotechnology is exciting, both from the point of view of what is existing in nature and what can be done, you know, in terms of some of the applications. But let me come to a little bit closer to the kind of things that we do in our lab. We make nanostructures, we assemble them in order to create certain structures. And what are the challenges and opportunities in this? So one of the major point of view here is, how do you assemble this humongous number of nanostructures to make something useful, or to at least create well-defined. It's a little bit like playing this Lego game. And many of us have already done this, and you know, the smaller the pieces are, the more complicated it gets, right? But of course, the smaller the pieces are, the more flexible you have in terms of. So nanotechnology is, again, it's basically a Lego game, but with pieces that you cannot really see. So you need to either, you know, use magnifying glass in the sense of a large microscope, or you need to figure out some boundary conditions that would allow things to assemble by themselves. You know, we call it self-assembly, or maybe we call it sometimes directed assembly. So you create environments where these structures or these pieces can assemble without you having to put these one by one. So that's a tricky part. And here is an example where many years ago, we were able to assemble carbon nanotubes in these vertically aligned arrays, you know, a large number of them, by essentially preparing a substrate with the right kind of catalyst and using to deposit the nanotube. Of course, you know, these are not as perfectly aligned as one would like, but there is a significant amount of alignment that allows you to call it, you know, vertically aligned. And what one could do with something like this? So again, coming back to this gecko, we were able to create, using these aligned nanotube structures, these strongly adhesive surfaces. In fact, artificial gecko surfaces. And we were able to kind of show that, by engineering the right density of these nanotubes and the right patterns that you can create by post-processing or post-growth, we could mimic the gecko tapes and build very, very interesting artificial adhesive tapes. So that's an interesting example of why one would want to engineer nanostructures in a particular order. Here is another. We were able to also show that with, again, engineering the density of these nanotubes, we were able to create a surface that has enormous amount of light absorption. In fact, we were in the Guinness Book of World Records to show that a layer of nanotubes would absorb more light than any other structure that has ever been made. So again, you can see we were also in things like Believe It or Not, young people to be attracted to science. We could, in fact, by designing nanomaterials, build these type of interesting structures that has both practical value and excitement value, motivational value. But if you go further and think about creating all these structures in 3 dimensions using nano scale as the building block, then you start to see, what kind of challenges you face. In fact, I think the holy grail in nanotechnology is the scalable manufacturing of nanomaterials from building blocks that are nanoscale, with control of structure, composition, and hierarchy. And even though we can say that this can be done bottom up, there is no real scalable way to make this happen. For example, let's say, instead of this, simply aligned van der Waals kind of structures that I showed you before, we want to build something like this at the nanoscale. Can you actually do this? The answer is right now, no. I mean, first of all, to make junctions between nanotubes is really a problem, because you have to break bonds and build bonds again. And secondly, how do you really do this type of architectures with the periodicity at the nanoscale? There isn't any such method today that you can do this. And if you are able to do this, here is a theoretical prediction of certain types of carbon-based structures that would look very different, and also that would be enormously useful. There are, if purely carbon, we talked quite a bit of carbon in different modalities, but if you could build these type of architectures, you can make carbon that is magnetic, you can make carbon that is extremely conducting, carbon that is insulating, in some sense. So I think the question is really, it's already known by theory that certain type of structures would give you certain properties, but today's technology doesn't really allow you to make these structures at the scale. And again, dimensions are important. You can make these at larger scale, and I'll show you one example of that. But to make this at the scale and the structure that you require is still a major challenge. But this is where the future is going. How do we do these type of architectures? Now, as I said, at larger scale, we can easily do this. The same structure, if you are not worried about the scale, we can print these. 3D printing or additive manufacturing has become very popular today. And we have been able to print all those geometries that you saw in the previous slide to be able to print them with different materials. And of course, these structures are also interesting in terms of stress transfer and so on, or transport, gas transport and so on. But of course, it is still not at that scale where the fundamental properties will change. Because as I said in the beginning, it's a combination of structure and dimension that ultimately brings in this type of major changes in the physical properties. But these are also interesting aspects of how some of the models that are described at the nanoscale could be translated to larger scale so that you can create some interesting features. I mean, people have done work in order to make these 3-dimensional interconnected architectures, but not with the periodicity that you saw. So by using certain catalytic techniques, you can actually weld 2 nanotubes together, you can create junctions, and you can create 3-dimensional structures. For example, this sheet of carbon that we made in our lab is all interconnected nanotubes, but with no periodicity, because that is difficult to control, right? So, and these are, again, very porous membranes that are very strong because they're interconnected nanotubes. They're used for example, electrodes in energy storage, batteries. You can use them for membranes, for filtration. So I think there is a lot of activity today in trying to create nano-structured materials or nano-engineered materials, which could be useful. But again, what I'm trying to say is that in order to reach the kind of clear periodicity and control of structure, that is still quite a challenge. Of course, we also do a lot of work at the very nanoscale. So it's one thing to actually make a solid structure, large structure with a lot of interconnections, because it's hard to say what these materials would behave. So one has to go and look at these individual junctions using techniques that people have developed in their labs. For example, you can actually look at a nanoscale junction in situ in a microscope and look at the structure as well as the change of behavior. For example, when you load it, how does it change? You can actually create a stress strain curve within that junction. So there's a lot of work that is being done in developing tools that allows you to do nanoscale observation or experiments at the nanoscale. And that is as important as the things that we do in terms of creating materials. And once you have some understanding, you can actually use the theoretical predictions to kind of broadly predict what these kind of materials will behave. And it's important because you need that data. And today, theory has broadened its other areas like artificial intelligence, machine learning. So all these things come into play when we are trying to understand a complex structure and look at nanoscale properties and how that translates into macro scale properties. Here is an example, very similar structure, a three-dimensional scaffold that are made from interconnected graphene instead of nanotubes. And I just wanted to show this because it shows enormous amount of flexibility. Not only that, this flexibility or this elastic nature of this kind of structures show all the way from cryogenic temperatures close to liquid helium temperatures. Actually, that's remarkable, something that is showing elasticity at that temperature, all the way to 1,000 degrees or so. So, if you can, again, engineer structures with nanoscale elements, which are specific, fascinating properties, and build larger structures, which could be useful in practical applications, then you can extract these significantly improved properties. I don't think there's any material that shows this kind of thermoelasticity range. So that, again, shows how we work from the nanoscale and go all the way to making structures that could be. Let me talk a little bit about interfaces. And again, I don't have too much time, so I will go quickly on some of these ideas. And again, one of the things that you saw in early slide is that as you break it down to smaller and smaller pieces, the volume of the interface increases dramatically. And that is a plus, and that could also be a minus. It could be challenging because sometimes processing becomes very difficult. The same amount of material, if it is in the micro scale, you can easily disperse it in a matrix, but when it is in the nanoscale, it becomes enormously difficult because of the large surface area and hence increase in viscosity. So interfaces are important, right? Interfaces can also be an advantage because, as I said, you can build hierarchy in a much better way. You create surface functionalities, you can change modify surfaces at every level. And as you have more and more interfaces, you can introduce the value added by these interfaces. Just like the abalone shell that I showed you. It is only the interfaces that is allowing you to make a material that is much tougher. So playing around with the interfaces, designing the chemistry of the interfaces, modifying the chemistry are all exciting part of this whole nano engineering. Again, there can be many interesting examples where chemically functionalized nanomaterials can be put together in different ways through cross-linking and so on that makes materials stronger, that materials more interesting, and designing the actual final product. And nanotubes is not just the only example. There are many, many examples that essentially has tried to build larger structures from individual building blocks. This is a great example of a cluster clusters that have been put together using these chemistries at the interface. So today you can build this really macro scale cluster assembled material, really atomic precision. These clusters can be essentially very, very precise. And when you put together, you have enormous flexibility by changing the interfaces to change its electronic properties, change its optical properties. So there's a lot of material science that is being done to create these fascinating architectures. In addition to that, you could also think about changing the interface to your advantage. So if you are thinking about a polymer composite where nanomaterials are added to the polymer, by changing this interface through chemistry, you can either make it very strong or you can make it very weak. And both have, again, advantages. If you obviously in a structural composite, you want it to be very strong. So you use the right kind of chemistry. And again, I want to emphasize the reason why this works very well at the nanoscale is that you have enormous amount of interfaces, and the impact becomes much, much larger. So you can, I will give you one example of a strong interface and one example of a weak interface. The example of a strong interface is the structural composite that I mentioned. You want to have load transfer, which means that you have very good interface. But if you don't have very good interface, you can also use this to your advantage. So this experiment shows that when you apply load to this weak interface material, there is a lot of sliding, there's a lot of dynamics going on at that interface. That allows you to absorb energy when you're loading. So this type of composites can be useful in cases where where you need vibrational damping. Again, you damp vibration by absorbing energy into the structure. So this type of weak interface materials could be perfect for that. So again, by engineering the interface between nanoscale objects and the matrix, you can play around with what kind of application that. And here is an extreme example of that, where we were able to engineer the interface in such a way that as you load the material, it actually starts to strengthen because the interface starts to evolve in certain direction. So you can think about making self-stiffening material, which is fascinating. In fact, many of the structures that you have in our body, like bone, is self-stiffening. That's probably due to some biological additions, and it's a living material like your bone. So that is slightly different, but you can think about synthetic materials that are self-stiffening, self-healing. There's all kinds of fascinating attributes you can give by designing and engineering materials. Now, the building blocks itself can be quite complicated. I mentioned about clusters or nanotubes, but you can also have bifunctional or multifunctional nanostructures that contains multiple components. So here is an example of a golden nanotube. And the reason why I'm showing you this is that this is very, very nice nano wire, because on the one hand, one side you have gold, which is hydrophilic, and the other hand you have a nanotube that is hydrophobic. So one could think about assembling them into a solution, and it forms these interesting globules where these nanowires assemble in a mixture of, let's say, oil and water. It's a micellar type of assembly. Chemists would know what that means. Essentially, when you have hydrophobic and hydrophilic structures, they assemble accordingly in solutions that contains oil-like and water-like medium. So you can create, for example, a golden sphere, but you can reverse the solution and create a black sphere with the same material assembly by changing creating the reverse kind of solution. So again, these have implications. So what I'm trying to say is this idea of reconfigurable assembly might play very well in cases like drug delivery. For example, let's say you create a capsule with multi-component nanostructures. You embed a drug and you target a particular area, and then you essentially deconfigure or break up the assembly by some external means so that you can deliver the drug. So there's a lot of active components that might be one might be able to create using nanoengineering, and that's quite fascinating. The other possibility is to create nano devices. Of course, electronic devices are very common. But people have now started to build devices like a battery or solar cell at the nanoscale. And of course, all these things need the right combination of materials and the right kind of engineering at the nanoscale. So here is an example where you have the anode, the cathode, the electrolyte, all these components that are important for a battery, all engineered into a nanospace. And they work very well as an energy storage device. And again, we work quite a bit on batteries and supercapacitors and things like that, which is useful for energy. And our goal is not just to make better in terms of energy that you can contain, but also different forms of energy storage devices. So we make flexible batteries that can be wrapped around, structure. Or we are interested in making things like paintable batteries, battery that you can paint anywhere, right? So utilization of these type of materials allows you much more flexibility in building these type of devices that have much broader applicability compared to the typical devices that you see. So those are exciting things as well. And one more topic that I will cover quickly is the fact that you can go to the limits. And again, that is what nanotechnology is all about, going to the limits. So, I already mentioned about single atom thick material like graphene. And if you have that, again, Richard Feynman is quoted widely for pretty much everything. And here is one example where he was fascinated by these layered materials and the fact that if you can pick up these layers one by one, then you can combinatorially build very different types of materials. So, and again, this is a basic concept from a materials point of view. If you can make these building blocks or extract these building blocks, then you can put it together in various ways to make fascinating new materials. So here is a picture from physics today, showing that one is able, if you can actually extract individual layers, do this Lego game and build up various fascinating structures. There are many, many materials that allow you to do that, all the way from metallic to semiconducting to insulating. And again, this is too crowded. Don't worry about the contents, but end of the day, many of these things, what we do has to be utilized. And that is precisely the reason why we do many of these things. So, semiconductors, I mentioned many times. Here is an example of a very fascinating type of device. We call it the tunnel FET, which is possible because you have materials like this, because the traditional silicon materials would not, create the right kind of devices because of some fundamental thermodynamic reasons. Electrostatics, there are many reasons why when you scale down things may not work very well. But using these type of new materials, for example, the reason why something like graphene is interesting is because there are no broken bonds in that single layer, right? Whereas silicon, if you make very thin, you will have so many broken bonds, and that will interfere with some of these device characteristics. So I think there is also, I didn't emphasize it too much because we're mostly looking at materials aspect. There are also devices and other things that would be very, very much benefited by development of these type of unique nanostructures. And again, as Feynman said, what material scientists like us are interested in is to put these things together in various ways to make new types of materials. So I can I can take graphene and I can take another material that is very similar, extract these layers and put them one after the other, in a periodic manner. And that would be an entirely different type of layered material. So again, this is the same Lego thing that I mentioned. How do you have n number of pieces, and then how do you really put these things together? And again, you have to do a lot of characterization to understand these kind of stacking. We can also do engineering in this individual layer to make structures and an entire device within these. And again, imagine today we are able to actually make an entire full device, a fully functional device, by engineering a single atom thick material. Same thing, the semiconductor industry is looking at 7 nanometer devices. And there are billions of these devices in the chip that you get for your cell phone or for your computer. So it's all about how do you essentially engineer these structures together, whether it is top down or bottom up. It's a fascinating long-term perspective. How far can you go? Can you go to the molecular scale? If you go, are there tools available where you can play around with things much less than 7 nanometers in top down? Or do you need a bottom up approach to it? And again, you can make really fascinating materials and look at them atom by atom. Here is actually an energy filtered electron microscopy image that shows a single unit thick layer of an alloy, which is made of 4 different elements. And these color combinations, what you're seeing is essentially columns of atoms. Essentially every atom you can tell where it is and what atom it is. That's again the progress made in tools like high resolution electron microscopy, and this goes hand in hand with most of the developments that we have seen in nanotechnology. And some of these materials can also be converted into other types of forms like quantum dots. I'm going to skip some of these, but what I want to say is that some of these quantum dots have been used for very important reactions, things like carbon dioxide reduction. Carbon dioxide is going to be a major thing. I'm sure that it's talked about in Europe and other places. It's going to affect our future environment. So nanotechnology is also being looked at in designing catalysts, designing new types of absorption materials, both for capture as well as conversion into useful fuels. So again, it's a broad field, and this is actually taken from an NS survey that says that we have kind of ended the second phase of this nano revolution. We have been able to make a lot of these materials. We have been able to design and engineer some of these structures, both from top-down and bottom-up approaches. Scales. And you're going to see probably a technology divergence where many of these things start to get integrated in the next phase. I don't know, 2030 is the end date, but essentially, this is going to, you're going to see more and more integration of nanomaterials into many technologies that will be very valuable for us, whether it is energy storage, energy conversion, semiconductor electronics, or nanoelectronics, membranes, water desalination. I mean, there are all kinds of technologies that allows the implementation of nanomaterials. And I would say we are still early stages in really, atom precise engineering, but I would certainly say that we have understood a lot in the last 2 decades and how certain materials work at the nanoscale and how you can assemble these things. And of course, in the future is going to be an intelligent, responsive kind of environment. You can, sensors embedded everywhere, and obviously, these are nano. I mean, we have already seen the effect of the pandemic. Right? I mean, if you can have sensors all over the place, real-time monitoring of all these issues, solve a lot of our problems, right? And healthcare is a major area where nanotechnology is being pursued, both in drug delivery as well as biosensing and so on and so forth. So I think we are going to see a world that has full of responsive components and elements, and that many of those things will be enabled by nanotechnology. And let me kind of finish. I thought I'll pick a quote from Cervantes because that is probably relevant here. And science is like anything else. I think it has to be diffused into the public domain. We all have to be prepared, and only then we understand the importance and relevance of science. And to be prepared is half the victory, really. Whether it is scientists or whether it is non-scientists, I think technology and science has contributed immensely to our well-being and our society. And I think it's very important for us to be at least aware of what is happening and what it is for us in the future. End of the day, it is all the taxpayers' money, as they say, that goes into furthering. But it is all for your own good. I mean, if you can control this, if you can actually mold the future progress technology-wise, I think it'll be an amazing world. And as a scientist, I have to say, I keep still excited, for new ideas and new problems, and it is more than just a job for us. I think it's about being completely consumed by this job, and I think it has been a real pleasure to be in this field, I have to say. So thank you again. I have a couple of more slides. It's mostly quotes. The world is going to look very different, and I need to also thank people, and we have a very multidisciplinary group of people coming from almost 15 different countries. And that is another, speak pretty much the same language, where you come from a remote part of Africa or Europe or United States. Thank you very much. I hope, broad enough for a large section of the audience. And, nanotechnology is, again, a big field, and you can keep talking. But I think what I wanted to mention is the materials aspect of things. What are the challenges and opportunities that future generation has for materials in terms of nanotechnology? Thank you. Ramon, you can hear me, right?
Yes, I can hear you.
So should I stop share?
Yeah, we can start like that. No problem.
Okay.
Well, first of all, I would like to thank you, Ajayan, for your kindness in agreeing to participate in this talk that we could define for all audiences, okay? So as an introduction, I would like to say that I met Ajayan for the first time in Colombia when the organizers of the meeting, Expo Engineering, very kindly invited us to give a conference. And well, the truth is that when you have to give a conference next to someone like Ajayan, with tremendous scientific impact numbers only achievable by really very few researchers, you feel some pressure. And I decided to present something different at that time. And I gave my lecture presenting practical cases in the use of nanomaterials with some success. Well, when I say success, I mean that the results have allowed the development of some products of special importance. No? At the end, I had the opportunity to talk with him, and I was delighted to see that Ajayan was very interested in our practical results with impact, for example, on the new CERN particle accelerator and other interesting things that I presented. Well, we have the opportunity to talk several days, and I realized that this man of such wisdom who had given such a good speech today was at the same time a tremendously humble person. Believe me, he's even better person than scientist. So thank you, Ajayan, for that. So the truth is that we spent very, very pleasant days in Colombia, and I have always had in my head the idea of tricking Ajayan so that he will come one day to the SIG for a season to do whatever he wants and enjoy our country, which, well, by the way, you already know perfectly, okay? So today, instead giving a talk, I'm going to ask Ajayan a series of questions that I think they may be of interest to all who are listening to us today. But before going into questions related to your talk, I would like to ask you about how you have handled this terrible situation with COVID-19 in your research center, and to what extent it has influenced your work, and what is the current situation, please, Ajayan?
Thank you, Ramon. Thanks for all those kind words. I really appreciate it. You are a good friend. I would appreciate any chance to come and hang around with you. Hopefully we'll do that in south of Spain one day. As I said in the beginning, this year has been a very interesting and difficult year for many of us. The COVID in the United States, as you can see, is actually going through a second wave, and it is really, in a pretty bad situation. But a private university like RISE, I would say, has done a remarkable job of handling the situation. We had a quick breakdown, a lockdown period in the early part of the spring, but we started to open the labs somewhere in May, and ever since then it has remained open. The labs are open, and then the fall semester started, and we gave pretty much all the students the opportunity to either take classes in person or by online, and many classes are actually dual mode. So for example, the class that I teach, I go and teach in the class in person. There are just a few students there, maybe 3 or 4 maximum. Rest of them are online. Just to kind of show that I mean, you can manage the situation. And, essentially, the labs are all pretty much operating. We had to do several shifts because of, the social distancing. You're only allowed, a certain number of people per square feet. And we, as faculty and students on campus, get tested every other week to see if there are any symptoms. We trace folks who have shown symptoms. So I think, everything that is possible that has been done in a small place like RISE. Of course, when the universities get bigger, maybe the challenges are bigger, and many of those universities, I think, are purely online. Outside the university, my younger child goes to school, and she has been online pretty much for the whole year. So there are multiple levels of challenges when you face a situation like this. The students themselves have slowly adapting, but many of them have difficulties adapting to the situation. So there is a layer beyond what we can see, and we are actually starting to see some difficulties. Of course, there's counseling and stuff like that goes on in the university, and they have enough and more help that they can go to. But it has been difficult for all of us. I mean, people like us who used to travel quite a bit are stuck at home. I mean, maybe, there are certain positive sides to it. I think we are all as busy as we used to because of all the Zoom calls that is allowed and so on. So I think in my opinion, is that we have learned quite a bit from this pandemic. And, the life is not going to be the same going forward, whatever happens. I'm very hopeful that there will be treatments and so on coming months. But I think we have also learned many important lessons that, we could manage a lot of things without traveling, for example, right? I mean, of course, there is there's a great thing about travel, but many of us were overdoing it. And so I think, it's kind of shown us who we are and what we can do. But in terms of the actual productivity and actual working, I would say that places like RISE, we are pretty much back in terms of most of the labs being open, testing going on regularly, and making sure that everybody is well and good.
But if the next year we can move and we can travel, I think everyone will try to go everywhere. This is going to be quite difficult to manage, for sure. Wow.
Yeah.
Yeah. So, this talk, as you know very well, is addressed to the general public. So I'm going to ask you quite general questions, okay?
Sure.
So my first question concerns the huge amount of the huge investment in nanotechnology and nanoengineering that has been made over the past, 20, 30 years already. Is crazy, eh? And I would like to ask you if, in your opinion, society has already benefited in some way from this enormous investment. And on the other hand, in what space of time and in what field do you consider that nanoengineering will promote new technologies that will improve our lives? Okay, yeah. I think it's a difficult question, okay, but well.
Well, it's a fair question. I think, all of us needs to understand what the result of many of these investments are. But, you have to realize that, technology is built on science, foundations of science, and, they feed into each other. It's kind of a closed loop system. And many of them have latent periods, from the beginning of a technology innovation to final, product development. And I think in some sense, we have become kind of impatient in recent times. If you look at traditional translation of research, it has taken, several decades for many of the technologies to blossom. But, I think going back to specifically nanotechnology, there is already advances that has, impacted all of us. I kept mentioning the semiconductor industry. If you look at devices, they're all pretty much nanoscale, and it has been result of a huge investment in nanotechnology, and how development of tools that can go to that scales, and also understanding things at the nanoscale. There are many other areas that, as I said, will be, in the next phase impacted quite dearly. Energy is one of them. Already batteries and supercapacitors are driving our technologies in a big way, and hopefully, we will see this transition to EVs and so on, in the next many decades. And that, many of them have serious impact from nanomaterials and nanotechnology-enabled research. So, and again, as I already mentioned in my talk, things like environment, CO2, methane. I think these are all fabulous opportunities for us. Of course, there's a dark side of things, and that's why we want to change over. But, catalysis, certainly a nanotechnology thing. And in the future, I think one of the areas that I hope would benefit significantly is healthcare. And, whether it is, devices that is useful for healthcare, like sensors or actuators, but also, things like drug delivery. How can, again, we already know things like CRISPR technology it's essentially a nanotechnology in some sense, right? It's basically gene editing. So those things are certainly poised to have huge impact. Water, we actually have a big center at RISE called the Nanotechnology-Enabled Water Treatment. Again, trying to find catalysts for disinfections, trying to find membranes for desalination. These are all essentially nanotechnology things. And of course, in the future, the transition to quantum technologies or quantum materials is going to build on whatever we have understood in the area of nano. So, science is a continuously, moving target, right? We build on the previous accomplishments. And I think many of these research, essentially coming from this huge investment that you mentioned, is going to mold, the future technologies and the future, focus in science like quantum materials. So, again, we do a lot of fundamental research, and we always believe that some of these things will get translated in the end. And I know, Ramon, that you do very practical things, and I think these are two faces of the same coin, right? Without one, you can't have the other. So I think I have strong views that nanotechnology will have a huge impact in many technologies to come. Again, it's more of an enabling technology because, end of the day, nano is nothing but a length scale. And, but I think it will have big impact, and we're already seeing that.
And one question concerning the investment. Well, today is the public sector who is making this investment. In USA, do you have also a private investment? There is some kind of small balance between public and private investment?
Yeah, US is a very different ecosystem, right? I think the way it works is in the big industries, of course, give funding to individual labs and so on to some extent. But there is a strong emphasis on entrepreneurial type of approach where the money flows in, of course, from private sector, in a different way. It's not the same. I'm sure that this is also happening in Europe. And, I lived in Japan for many years, and things are quite different. I think the big industry was involved with academia in creating this kind of synergy. But US is all about, individual entrepreneurial spirit. And, many of these technologies has been spun out, some of them survive, not many of them survive, but that's the nature of that whole ecosystem. But I think, a lot of the money that the private sector has created, the wealth flows back into the ecosystem. And that's how I think the US has worked.
And, for sure.
So it's a different type of investment, but at the end of the day, it is private money.
Yeah. I would like to ask you about a bit about your history, since it seems to me that you have always been in the right place in the right time, because I think you have been involved in the first experiments aiming at growing nanotubes. This is right? You were in Japan when this...
Yeah, again, I mean, I don't think I've been at the right time at but certainly,
probably you were the person with that. Huh?
Yeah, certainly. I was very lucky to be in Japan at that time when the nano came out. I mean, that kind of defined my career. And, this happens to many of us, maybe at early stage or later stage. I think there's so many opportunities, right? Sometimes, again, as the quote says that I showed you, being prepared is probably, half your victory, right? If you're ready to take an opportunity that comes along, then you're at the right time at the right place, right?
No, but I was surprised to see that you were in Japan. Well, you are living in Japan, and they obtained the Nobel Prize. You were in Paris. You were working with them, and finally they obtained a Nobel Prize. What are you doing?
Well, I mean,
so I was surprised.
I'm going to work with you, Ramon, in the future. So how about that?
Okay. So we see in scientific magazines and on television many times that the famous figures made from atoms that you show, that we place one by one atom forming more complex structure. And apparently it seems that you have an atomic printer in the lab, that allows you to do anything. Well, I know that this is not the case, and that is much more complicated. But even if that were true, okay, I wanted to ask you about the problem that exists today to go from the lab to large scale production. You have been talking about during your presentation, and how can we imagine a factory in the future for nanometric devices, and what special environmental conditions are needed for this purpose? Because it's quite difficult to work in these conditions. So how can we imagine a factory on this kind of sensors and things like that?
I think it's a really very good question. I think one of the limiting factor in translational research in nanotechnology has been this lack of perhaps collaboration and understanding, from various interdisciplinary fields to build such a factory. I mean, I suppose when you say factory, it's essentially the mechanism that ultimately translates these fundamental discoveries into practice, I suppose. And there, I would say that there are both intrinsic issues as well as extrinsic issues. I mean, intrinsic issues, for example, I think we have struggled from a materials point of view with reproducibility, with scalability, and things like that. And intrinsically, many of the nano processing that we do are, suffers from this variability, right? I mean, even today, it's a real challenge to make, a ton of material that has very tight distribution of particle sizes or structure, right? But perhaps, this is basic to, the nano materials or nanotechnology in general. If you look at biological systems, you take two cells, you see similar structures in each of the cell, but they're not exactly same in size or shape. There's always this variability that is adaptable to the system. Yeah. So that aspect, and perhaps one has to still think about how to deal with this intrinsic variability that exists in these type of materials. And the other is development of tools and so on that is needed very much to create for example roll-to-roll manufacturing or continuous production methods. And I think over time a lot of these ideas are coming together, and perhaps, as I said, the next phase will be a realization of what is really the right technologies and how that can be translated, the combination of computational, theoretical methods, maybe machine learning kind of thing, and a better understanding of, what kind of technologies are needed for integrating these nanomaterials. We would probably see better I think it's very important to have these large-scale centers and precursors to these factories that you mentioned, where people with different background can come together, including industry, right? And build the next generation of factories, right, for nanomaterials. And I still think that we are still early in the stage of understanding, because it's in many ways it's a paradigm change, right, for materials when they become so small. It's not as simple as scaling down. It's more than that.
Okay. So you said that nanoengineering is a branch of engineering that explodes the unique properties of nanomaterials related to size and quantum effects, and that we try to design and manufacture novel structures and devices that possess entirely new functionalities and capabilities, and of course, which are not obtainable by macro-scale engineering. Well, please tell me now that we are alone, what is the most secret development that you are developing in your lab? And that if you tell me now, will it mean that you will be fired from your university? Well, okay, tell me another one. Tell me another one, but tell me what are you doing exactly?
We don't really do anything secret, fortunately, right? I mean, we are all public domain stuff. I mean, we publish whatever we do. But I mean, again, maybe I can answer what kind of things we do in our lab in addition to what I mentioned. We are very much into energy storage that I said.
I'm going there.
Batteries that are flexible, high temperature, high energy, all that stuff, and a lot of people, of course, not just us. We are interested in CO2, for example, 3D printing. For example, the latest work that we started is a project based on diamond electronics. So we are actually starting to grow, diamond for the next generation of ultra wide bandgap electronic materials. So again, I think our group is pretty broad in its reach, and we do multiple things. But as you asked,
you don't feel the pressure from companies to develop the specific things. No. Still,
yes. I mean, for example, 2/3 of my research is supported by industry.
Okay.
So we do have some short-term as well as some long-term, but normally most of the things, even what the companies involve us in doing, is something that could be published, something that could be, where the students can be trained on rather than just
open science. Yeah. Okay, thank you very much. Well, this morning I was remembering with Professor Moya, my friend Professor Moya from CSIC, that delivered a conference last week. A conference delivered by Tony Tomsia from the Lawrence Berkeley Laboratory some years ago, where he started to present a message to the future generation of scientists, okay? And he included a question that was, what remains to be discovered? And he used a sentence of, Sir John Maddox, the editor of Nature, for 22 years. And he said, let me, what is it? He said, the scientific record of the previous centuries suggests that excitement in the years ahead will spring from the answer to the questions we do not yet know enough to ask, okay? And Professor Moya said, well, you have to ask, Ajayan, if you have today some open questions for the future, which are these questions? What do you think?
Well, I mean, if I knew what are those questions, but the point is really interesting, right? It is said that if you compare with what we know and what we will know in the future, you'll be humbled, right? Essentially, I think we are so early. I mean, if you look at the major scientific developments in humanity, this probably happened in the last 2 or 3 centuries, and maybe even the last century. So that's such a short time scale in of the universe or whatever. So I think it's hard to tell. I mean, I was also reading somewhere that many years ago, centuries ago, people are asked to kind of predict what kind of devices and things will be there in 500 years or 200 years. And, they all predicted things like, flying stuff, when there was no planes at all. But then they were asked to kind of sketch what they looked like, what these things looked like. And they sketched very strange things like flying balloons, So I think the details are probably very difficult to kind of predict. But I think, we are seeing some amazing things that is happening today. I mentioned about gene editing, for example. That's going to revolutionize our lives and society completely. People are talking about, immigration to space, right? I mean, we are already seeing SpaceX and NASA sending people to space. I mean, so I'm absolutely sure that there will be a time when we will colonize space, and that, the challenges will be very different when we do that, both in terms of materials and technologies. So there are many, many things that are quite amazing, and quantum technologies, quantum computing and things like that are just the cusp of maybe happening. It might still take a few decades, but so it's always a challenge. I mean, this is what we all struggle with, right? I mean, can you predict the kind of things that will happen 5 years from now, 10 years from now, 100 years from now? I mean, if 5 years is feasible, 10 years is a little bit more difficult, and 100 years is almost impossible, right? But you can kind of generally say that there are these things that are on the horizon, and we all will contribute to that.
But if you take into account that 15 years ago, we started with internet, and our life changed completely. Our society changed completely. And now we know that we have 15 different technologies arriving at the same time with the same possibility for change as internet. So
absolutely,
you can ask questions about that. It's practically impossible. Nobody knows what is going to happen exactly, because it's moving so fast that, well, I don't know, probably your brain can work thinking about what's going to happen in the future. But for me,
but I think that's the fascinating thing, right? I think the young generation should be motivated to be in STEM, because there is no better area of excitement that I can think of than science and technology, and to be part of that is what we should all be thinking about, right? I mean, and I think young generation somehow misses that, and maybe, I don't know about Europe, but the school curriculum, doesn't really motivate young people to be in STEM. And I think that's important thing, because I think the young generation is what is important really, to be part of such an exciting times.
And even because for me, another aspect of nanoscience that makes it very, very special, that is the length of scale of biology now. So we're talking about the size of proteins, of viruses. These are the nanomachines that make possible life, okay? So when we can start to match up technology with the length and scale of biology, there are, of course, great possibilities that we can start to think about, the typical concept of nanomachine and putting it into the body and target the specific type of cell, cancer, etc. Well, I know these are the reasons the scientists were sort of excited about nanoscience and nanotechnology, but the transfer of a concept or mechanism for living to non-living system is not trivial. And the most biological system currently exceed by a great margin, well, really thousands, the engineering nanotechnology. So, well, definitely you were talking about life is the most complex self-assembly, okay? But do you think, can we one day print, this is really a complex question, can we one day print a living being, a virus, for example? Why not?
Why not? I mean, I totally believe that we can do it.
You believe that. One day we will print a living being? My God, this is hard. But
well, I mean, again, I think the opportunities are tremendous, right? I mean, people are already printing organs and things like that. So, again, what amazes me is that we have achieved so much in such a short period of time, right? I mean, you mentioned about internet. I mean, 15, 20 years ago, right?
Yeah.
It's nothing. And the stage we are in is beyond, imaginable. So I think all these things, if the time is on our side, and we are we live as a stable society, I think all these things will happen. And again, it's hard to predict the time scale of some of these things, but I totally believe that it'll happen.
Yeah. Well, if you consider the ease with which biological systems transform or storage energy, for example, or the abilities to perform, as you saw before, the self-repair and to adapt of changing external conditions, or the way in which energy, entropy, and all the information are manipulated within the nanosystems of life. Yeah. I would like to ask you, where are we now exactly in these specific research lines? I mean, concerning, for example, now nanobiomimetics, for example, no? Because, well, really, everything is in nature, so we have to learn from nature. And what are you doing exactly in this field?
So, I mean, there are many things that related to biomimetics and how nanotechnology can contribute. I mean, I actually teach a course in biomimetics in my department. Of course, there are simple things like, Lotus effect and so on, which is easily implementable. And in fact, people have already implemented. Or I actually had a talk from one of our student groups about self-healing materials. And I think remarkable advances, particularly in things like fabrics, incredible biomimetic, self-healing structures that people have made. I mean, many of these 3D printed structures that I've showed you are essentially structures that we have been motivated from nature. All these Schwarzschites are, this radial area structures that, the exoskeletons of planktons that people have seen. So, nature is a great place to look at for motivation. I mean, we probably don't want to mimic as they are, because we have many, much more, much better freedom to choose materials and so on. I always say that nature has a small part of the periodic table available to them, whereas we have the whole entire periodic table. I mean, it's an exaggeration, but that is true. Many of the living systems and biological things get a few elements and they play around. And it's a great, I think it's a great avenue to look for frugal engineering.
Engineering.
Really, I mean, because, you look at things like bone and teeth and stuff like that, it's the same material in different morphologies and densities, So, but of course, these things have been evolved over long periods of time, whereas we are kind of impatient because, we are looking at 5-year, 10-year timeframes. But I think, again, it's a great area. It has been, as you said many times, difficult to completely mimic certain things because of the complexity. But certainly learn a lot and try to implement things in certain ways. And we are very excited about biomimetics.
I love it, yeah. So this is going to be my last question now, because probably you have a lot of things to do. For us, we have to go home to sleep.
Yeah, actually, I have another meeting at 1:30, so maybe a few more minutes and I can...
It's the last question.
And again, I want to say that if there are any questions, please email me. I think, I will be happy to answer.
So we always say that this research field involves truly multidisciplinary and international efforts, covering a wide range of scientific disciplines. And in your case, do you have such a multidisciplinary research group? Is really multidisciplinary also, or do you have mainly?
Absolutely. I mean, as I said, we have students and postdocs from about 15 different countries, and we have a lot of collaboration. Within the U.S., I collaborate with a lot of people in Europe, Asia. So again, I think this has become the norm these days, right? Many of these research works that you find exciting, they're all done through collaborations, both theory, experiment, different countries, different backgrounds. So I don't, I think with all this internet and easily doable things over emails and so on, online, there is no barrier at all. I mean, I can collaborate with you, Ramon, just as I can collaborate with somebody sitting next to
me. To go together to CERN, we are waiting, but
and
we have to do it.
We do want to see more folks actually coming from Europe to us. I mean, for example, at Rice, I hope there will be more of that synergy. But I think, I've always felt that one of the advantages and the real motivation that I've received for doing science is also this ability to be in different places, travel, meet people, and also stay in different labs and see how they work. I mean, that's certainly influenced my career for sure.
Okay, well, as usually, Ajayan, thank you for your kindness.
Thank you very much.
Suggestions, thoughts, your opinions. You are more than welcome in our country and in our institution. So thank you, my friend.
Thank you. And definitely, if there are questions, unfortunately, I have to go. Please send it to me.
So long.
I'll make sure I'll respond.
Thank you very much.
And great to see you, Ramon.
Okay.
Yeah, thanks, Gonzalo and everyone. Thank you.
Bye. Thank you. Thank you very much.
Well, okay, it's just a couple of words to say that we indeed received 3 questions from the audience, and we have noted them down, and we will take Dr. or Professor Hayan's word and email him for him to reply to our audience, and so we show our thankfulness for that. So Berta, please.
Okay.
It's been a pleasure to welcome Professor Ajayan in Brussels, even virtually. And thank you very much to Ramon, and thank you very much to Instituto Cervantes. It's a pleasure to organize an event with you, as always. And we invite the audience for our next talk. Will be the 2nd of December, and we will talk about inclusive robotics with Carme Torras from the CSIC Institute of Robotics in Catalonia, and with Rosa Montero. So it will be interesting as well. And good night, buenas noches, y keep in mind the utility of science. Thank you. Gracias.
Thank you.
Bye. Bye.
Thank you very much.
Adiós, Ana.
Thank you.
Adiós.
De la Torre. La.
Ajá, ¿cómo estás?
Ahí.
Están escuchando, estaba. Muy interesante. Muchas gracias. Muy buenas respuestas, pero muy buenas preguntas también. Un abrazo.
Gracias, Clara. Gracias, Clara, por estar siempre ahí. Gracias.
Adiós. Buenas noches.
A la próxima.
Adiós, chicos. Gracias.
Cerramos sesión. Gracias.